Welcome into the lecture of the open course on diffusion in multi-component solids. So now that we have gone through various techniques for experimental determination of interdiffusion coefficients in binary, ternary as well as higher order systems, today I would like to show you some examples from the literature in which they have actually determined the interdiffusion coefficients, and we will start with binary. I will also give one example each from ternary, quaternary and quinary. So, the examples of determination of interdiffusion coefficients from the literature. First, we will look at a binary titanium niobium system. This we worked for determining interdiffusion coefficients as function of compositions at different temperatures, and I have shown here one binary diffusion couple between pure titanium and pure niobium. So, on the left side we have pure titanium, right side we have pure niobium. The first figure here on top is the concentration profile. This diffusion couple was annealed at 1150 degree centigrade for 24 hours. As we can see, the diffusion depth on the niobium side is much lower as compared to that on the titanium side, and this indicates that the interdiffusivities in the niobium rich side are much lower compared to the interdiffusivities on the titanium rich side. We can see on the left side of the metanoplane x naught, the diffusion depth is about 400 microns, whereas on the right side, that is on the niobium rich side, the diffusion depth is less than 100 micron. On the bottom figure here, we have shown the interdiffusion flux profiles. The red one is for titanium, the blue one is for niobium. These interdiffusion flux profiles were estimated based on the Dayananda's analysis that I discussed couple of classes back. We can see, as expected, there is a minimum in the niobium flux profile and maximum in the titanium flux profile at the metanoplane. Again, as apparent even from the diffusion flux profiles, the diffusion depths are much smaller on the niobium rich side. So, we can evaluate the binary interdiffusion coefficients as function of composition over the range of compositions developed in the diffusion zone in this binary couple. So, at 1150 degree centigrade, the interdiffusion coefficients that we estimated can be plotted against a niobium concentration as shown here. We can see there is a big difference in the interdiffusivities on the titanium rich side compared to those on the niobium rich side. As we go from titanium rich side to niobium rich side, there is about 3 orders of magnitude difference in the interdiffusivities. Close to titanium rich side, the interdiffusivities are about 10 to power minus 13 meter square per second, whereas towards the niobium rich side they drop down to about 10 to power minus 16 meter square per second. So, there is a big variation of interdiffusivities with composition in this particular system, titanium niobium binary system. Next, we will consider a ternary example. This is again our group's work on titanium aluminum niobium system. I have shown 2 ternary diffusion couples which were assembled at 1060 degree centigrade for 48 hours. The first couple on the left terminal alloy is 65 titanium 35 niobium. On the right side of the couple, the terminal alloy is 74 titanium 16 niobium 10 aluminum. These concentrations are in atom percent. The second couple between alloy 1 and alloy 6 is shown in the bottom figure, the concentration profiles. And on the left terminal alloy, we have alloy 1 with 75 titanium 25 niobium. On the right, we have alloy 6 with 56 titanium 29 niobium 15 aluminum. In couple 1, we can see the interesting features. There is a minimum on titanium profile, there is a maximum on niobium profile. Correspondingly, there are also zero flux planes for titanium and niobium. I have not shown the diffusion flux profiles here. Now these two are the couples with intersecting diffusion paths. So if we plot the diffusion paths of these two ternary couples on the ternary isotherm, it will be like this, shown here. So the blue path is for couple 1,6, the red path is for couple 2,4, and we can see they intersect at one composition, and the composition corresponding to the crossover point is 69 titanium 26 niobium 5 aluminum. Again, all the concentrations are in atom percent. So we can determine the 4 ternary interdiffusion coefficients here by setting up 4 equations. So at the crossover composition, in the first couple we can write the equation for interdiffusion flux of aluminum and interdiffusion flux of titanium in terms of the 4 interdiffusion coefficients and the 2 concentration gradients. Now this is in one couple. We can write similar 2 equations in couple 2, and so we get 4 independent equations which we can solve for the 4 coefficients here, and those coefficients will correspond to again this crossover composition. In order to get an idea about what orders of magnitude the fluxes and the gradients are, I have actually listed the numerical values of interdiffusion fluxes in the left side table and of concentration gradients in the right side table here. So the fluxes you can see for aluminum and titanium in couple 1 are about 10 to the power minus 5. The units of flux noted here is atom fraction micron per second. So remember, when we write Fick's law equation, 1 tilde equal to minus d11 tilde 3 dou c1 by dou x minus d12 tilde 3 dou c2 by dou x. We assume molar volume to be constant. Now in this equation, C1 and C2 are the concentrations which are in moles per centimeter cube, and the flux unit so is moles per centimeter square per second. We can also express the concentrations in terms of atom fractions. So if we express concentrations in terms of atom fractions, we can write C1 Vm is equal to x1, that is the atom fraction or mole fraction, and so C1 would be x1 over Vm. So if we multiply both sides by Vm, we can express this equation in terms of gradient of mole fractions of the components, and so the unit of flux will change and the unit will be atom fraction micron per second. But for this we have assumed that the molar volume is constant, and we do this because it is easier to work with the atom fractions. And assuming molar volume constant, the volume fixed frame coincides with the laboratory fixed frame. So if we substitute these values of fluxes and gradients in the 4 equations here, we can solve and get the 4 interdiffusion coefficients, the values of which are listed here. We can see the main coefficient of aluminum is 1 order of magnitude larger than the cross coefficient DALTI. We have treated niobium as dependent component here, but the cross coefficient of TiAl is higher than the main coefficient of Ti, dTiTi, and it has a negative value. This means the interaction of aluminum on the flux of titanium is significant and it is negative, which means the interdiffusion flux of titanium is enhanced up the gradient of aluminum and is reduced down the gradient of aluminum. So, aluminum has significant interaction on the flux of titanium. This is what this indicates. We have also applied the body diagonal diffusion couple technique to evaluate interdiffusion coefficients in Quaternary and Quinary system. So, let us look at the Quaternary system first. We wanted to evaluate the interdiffusion coefficients in the iron, nickel, cobalt, chrome Quaternary system at the equimolar composition, that is at 25 atom percent of each iron, nickel, cobalt and chrome. So, we used C bar, that is the average composition, as the equimolar composition, which is shown here, and delta C0 was taken to be 10. So, based on this we could prepare 4 independent diffusion couple across the 4 body diagonals. So, only 3 are needed. So, we prepared the 3 couples, and on the left side plot here are shown the diffusion paths of the 3 couples. Remember, in Quaternary system we have a 3-dimensional composition space because there are 3 independent concentration variables, and so this is a 3-dimensional figure. So, Quaternary isotherm is essentially a 3-dimensional figure. You can see the 3 diffusion paths of the 3 couples, couple 1, couple 2, couple 3, they are intersecting at one common composition, and the composition uncertainty of intersection was less than 0.1 atom percent, which is well within the experimental error. So, we can set up the desired 9 independent equations and solve for 9 Quaternary interdiffusion coefficients at the equimolar composition, and we obtained the 9 coefficient to be as listed in this table here. We can see the significant interactions exist between nickel and cobalt. So, if we look at the cross coefficient cobalt nickel, it is 50% of the value of cobalt cobalt, D cobalt cobalt, the main coefficient. If we look at D nickel cobalt, it is positive and close to the value of main coefficient D nickel nickel, which means the nickel and cobalt exhibit strong diffusional interactions in the Quaternary iron nickel cobalt chrome system, and their interdiffusion fluxes are enhanced down the gradients of each other and reduced up the gradients of each other. Then we can also extend the body diagonal diffusion couple technique for a quinary system, that is a 5 component system, and we were interested again in the equimolar composition of iron nickel cobalt chrome manganese system, because this is the most studied high entropy alloy system. So, we prepared the 4 body diagonal diffusion couples required for estimating 16 quinary interdiffusion coefficients. The concentration and flux profiles of the 4 couples are shown here. At the bottom are the flux profiles, on the top are the concentration profiles. We can see interesting features in 3 of the couples. So, the second couple, you can see there are 2 zero flux planes developed for nickel. The third couple also there are 2 zero flux planes for nickel, and the fourth couple exhibits 2 zero flux planes for cobalt. Correspondingly, you can see there are maxima and minima on the nickel and cobalt profiles in the respective couples. So, the strong diffusional interactions are again expected based on this maxima, minima and the zero flux plane features. So, we evaluated the 16 interdiffusion coefficients and they are listed here. Very strong diffusional interactions are observed. If you look at especially D iron nickel, it is almost same as D iron iron, and it is positive, which means in this quinary system interdiffusion flux of iron is enhanced down the gradient of nickel and reduced up its gradient. You can also look at D nickel manganese, which is negative and same order of magnitude as main coefficient d nickel nickel, which means again the interdiffusion flux of nickel is enhanced up the gradient of manganese and reduced down its gradient. So, this way we can actually determine the entire sets of interdiffusion coefficients in various systems using the approaches that I explained in the last class, and in this class I showed you some of the actual applications from the literature. We will stop here for today. Thank you.